This is a phase diagram for a substance. This is just a generic shape of what that diagram looks like for a particular substance. I will show you some other phase diagrams for water and carbon dioxide in the following slides. So on a phase diagram, it is a pressure versus temperature. And the reason we're using this is because pressure does not always remain constant, so that does change. And when the pressure changes on a substance, the phase also changes. Also, you could look at it and say when the temperature changes, we know the phase also changes too, and that one we are much more familiar with. So on a phase diagram, there are three parts to it. One part, the farthest to the left, is always the solid phase. The part that is in the middle is always the liquid phase. And the part that's on farthest to the left is always the gas phase. Okay? So whenever you look at any phase diagram, the shape of the lines on there might be slightly different, but we always have the farthest one to the left is the solid, the middle segment or section is the liquid, and then the farthest one to the right is the gas. So this is what a phase diagram looks like. So it's looking at the three phases of a substance that are most common. Now, with this phase diagram, there are some different points on it. Right here, this point right here is called the triple point. So at the triple point, what does that mean? It means that it's at a state of equilibrium where all phases exist. So in other words, you would have a solid, a liquid, and a gas of this substance could all exist at that temperature and that pressure, whatever that is. This phase diagram does not have any values on it, so we're just kind of pointing out the main parts of it. Now, the other point on here that is significant is this point here. This point is called the critical point. The critical point is at extremely high temperatures and pressure. If something is at an extremely high pressure and temperature, we get a substance that is called a supercritical fluid. That's what occurs at this point right up here when we have extremely high pressures and high temperatures. The supercritical fluid is a fluid that is partially liquid and partially a gas. So it is a mixture of those two. So any phase diagram has those 2 points on it. It has the triple point. That's where the intersection of three different phases intersect. And then it has that critical point, which would be at the very highest value for a substance on the at a high temperature and a high pressure. So here's a phase diagram for water, and notice I have the critical point labeled on it up here, so that's where I get that supercritical fluid. And then I also have the triple point labeled right here. So at the triple point, I could have a solid, a liquid, and a gas all exist at those conditions. So those are both labeled on here. So now we kind of want to look at what happens if I change the pressure. So 1 atmosphere, this is about where pressure is. This is normal conditions usually. Our atmosphere is very close to 1 atmosphere. At sea level, that's what it is exactly. As you go up a mountain, that pressure would get less. So it would be a little bit different. So if we looked at an example of changing the pressure, so in other words, right here we're saying at 1 atmosphere, and if we're at 0 degrees Celsius, that would be the normal freezing point of water. this one, if we're at 1 atmosphere and we're at 100 degrees, that's the normal boiling point of water. Okay. Now, if we happen to change the pressure on a substance, it will change the boiling point and it will change the freezing point. So if I increase the pressure, so if I went up here, if I increase the pressure, this would be a very high pressure. Look at what happens. We have a lower temperature. So at this right here, then they call this critical pressure because it's super high. At this point right here, then my freezing point for water would be less than 0. It would be below 0, so water would freeze faster. If I went over here, let's say if I was looking at this point right here, so in other words, if I look, my pressure here was at 1 atmosphere, here it would be something greater than 1. If it's greater than 1, what happens to the boiling point? Well, let's look at this. This would be my boiling point then now, because here I'm changing from a liquid to a gas. So my boiling point, so that increases the boiling point. And the reason is because of this. If I had a beaker and it had water in it, we know that these particles are moving and they want to get free if heat is added to it. Now, in normal conditions, we have particles here, right? And those particles are kind of stopping this water from escaping. Well, if I increase the pressure and make the pressure greater, I have more particles here. So if I have more particles here in the atmosphere, by increasing the pressure, it's going to let this water take in more heat, and it's going to raise the boiling point so that it would boil at a higher temperature. If you did that, that means that your food would cook faster. If you increase the temperature at which it boils, it's going to, instead of boiling at 100, now maybe it's going to boil at 200. So it's going to be a higher temperature and it is going to cook food faster. The reverse could also happen. If you went and you had a low pressure, so this is my example of Mount Everest. The pressure there is lower, so if you went to a lower pressure, where this intersects the line, I'm going from a liquid to a gas. Right here, this would be the boiling point now because I'm going from a liquid to a gas. The boiling point would be lower, so let's say it's 90 degrees Celsius. So that means I could get water on Mount Everest to boil at 90 degrees. Well, since the temperature is lower, it's storing less heat. It would take longer to cook things. So if I was making pasta, I'd have to boil it for a longer period of time. So here's a phase diagram showing you for water, and all it's showing you is what's happening at each one. So across this line, this is where we get the change in phases. So if it is going in this direction where the temperature is increasing, because you're increasing temp when you go that way, you would get melting. If you did the reverse, went from a liquid to a solid, the temperature would be decreasing, you would freeze it. So they're just showing you the different stages or the different processes that would be happening as you cross the line, whether you're adding in heat by changing the temperature or if you're releasing heat by decreasing the temperature. So this is a phase diagram. It's just kind of highlighted with the different phases and then the different processes of either absorbing energy or releasing energy. And to look at one final phase diagram. So here's a phase diagram for carbon dioxide. This would be dry ice. So this is a substance we're somewhat familiar with. So they use dry ice, they set it out, and it changes, it sublimes right into a gas. It changes to a gas. Now, remember, 1 atmosphere is what normal atmospheric pressure usually is. It's right around that. And so at 1 atmosphere, if you look, we are going from a solid to a gas here. That is at about a negative 78.5 degrees Celsius. That's very cold. So that's why dry ice at normal conditions, if it is a solid, which it is here, this is its temperature that it is at. Okay? So in other words, it starts to sublime When it goes from a solid to a gas, they're at that temperature, so it's very cold. So dry ice is used to pack things and send it from one place to another. They're talking about, yes, they're going to use dry ice to ship vaccinations for COVID-19, because the one I think made by Pfizer has to be kept at extremely cold temperatures to store it. So this is where it is subliming. Now, if you change the pressure up to 5 atmospheres, so that's a lot of pressure, that'd be 5 times what the atmosphere is. Those conditions are not normally, they aren't seen. You could produce that in a lab, but it's not very common. You would get to this point right here, and this would be that triple point again, where dry ice could be a liquid, a gas, and a solid. Now, seeing it as a liquid, I've never seen it as a liquid, but it's possible to do that if you increase the pressure by a large amount. And then they talk about, notice, dry ice here, this segment right here for a liquid, that's not a very big segment. So dry ice doesn't exist as a liquid for much of the scale on here. So they're just kind of giving you an idea of the fact that dry ice would mostly be found as a solid or a gas. So this is just a good example of showing you another substance that has different values for the subliming or the melting or the freezing of it, or vice versa if you went the opposite direction. So it's the same thing. We always started with the solid over on the left, the liquid is in the middle segment, and the gas is in the segment on the right. So it's just a phase diagram. Phase means what state it's in. So they're showing you what state it's in under these conditions. You could also look at this by changing the temperature too. So you can either increase the temperature or you could increase the pressure, depending on what they're asking you to look at.